The video immediately takes the viewer right up to the sun. We usually picture the sun as a massive ball of fire, but it is actually a highly active magnetic environment. Driven by charged plasma and shifting magnetic fields on its surface, various types of eruptions occur. Two key terms are crucial here: solar flare, coronal mass ejection, CME. A solar flare is a sudden, intense burst of electromagnetic radiation from the sun, lasting anywhere from a few minutes to several hours. Its X-ray and extreme ultraviolet radiation reach Earth's ionosphere, triggering radio communication blackouts. CMEs, however, are different. A CME is a massive release of charged plasma and magnetic fields blown out from the sun's corona into space. This is where the story gets interesting. Imagine a CME hurled directly toward Earth. It doesn't arrive instantly. According to NASA, high-speed CMEs can reach Earth in as little as 15 hours, while slower ones may take several days. The core sequence of our story unfolds like this: solar explosion, CME released into space, journey toward Earth, collision with Earth's magnetic field.
Imagine scientists spotting it on satellite feeds, a massive CME heading straight for Earth. Earth isn't completely defenseless, though. Wrapped around us is the magnetosphere, a vast protective shield created by Earth's magnetic field that deflects most of the sun's charged particles. However, a powerful CME can severely disrupt Earth's magnetic environment, triggering a geomagnetic storm. According to NOAA, as the CME interacts with Earth's magnetic atmosphere, it dramatically alters the ionosphere, increases satellite drag, degrades GPS accuracy, and induces unwanted electric currents in long conductor lines on the ground. This brings us to a powerful reality. Earth's magnetic field is our shield, but when a massive solar magnetic storm strikes that shield, our technological civilization hangs in the balance. Yet there is a captivating twist to this storm. It creates one of nature's greatest spectacles. The exact same charged particles colliding with Earth's upper atmosphere ignite the night sky with What happens if the GPS on your phone suddenly goes dark? Let's address a major misconception first. A solar storm does not mean the entire internet will simultaneously vanish. The real impact depends entirely on the specific technology involved. High-frequency HF radio. Solar flares release X-ray and extreme ultraviolet radiation that suddenly alters Earth's ionosphere. This causes high-frequency radio signals, 1 to 30 megahertz, on the sunlit side of Earth to degrade or suffer complete blackouts. According to NOAA, space weather disturbances alter or block these transmission paths, directly disrupting aviation, maritime communications, and defense systems. GPS navigation. GPS signals must pass through the ionosphere to reach receivers on Earth. When a solar storm creates turbulence in the ionosphere, it bends and delays those signals. This leads to reduced location accuracy, navigation drift and errors, loss of signal lock. NOAA confirms that severe space weather degrades GPS GNSS precision, posing operational risks to commercial aviation, maritime shipping, precision agriculture, and emergency services. The Internet. Rather than leaning into sensationalism, the reality is nuanced. The entire internet will not instantly disappear. However, modern communication networks heavily rely on satellite timing systems, radio backhauls, and vulnerable electrical power grids. An extreme space weather event creates indirect ripple effects across these interconnected networks, causing localized outages and system instability. Distinguishing these real-world mechanics keeps the narrative grounded, accurate, and far superior to standard internet clickbait.
A massive portion of today's invisible infrastructure orbits high above Earth. We rely on satellites for GPS and navigation, global communications, weather forecasting, Earth observation, scientific research, precision timing systems. During severe space weather, these satellites directly absorb intense radiation and high-energy particles. NASA notes that solar radiation can damage satellite electronics, trigger system glitches, and cause long-term degradation to solar panels and sensitive instruments. Yet, there is an even more fascinating physical impact at play: atmospheric drag. When a geomagnetic storm hits, energy absorbed by Earth's upper atmosphere heats it up, causing it to expand outward. This expansion dramatically increases atmospheric density in low Earth orbit, LEO, subjecting satellites to heightened atmospheric drag. The cascading effect unfolds quickly. Increased drag on the satellite leads to orbital speed drops, and altitude decays leads to operators must fire thrusters to take corrective maneuvers. NASA highlights this drag increase as a primary operational hazard for LEO satellites during space weather events. A solar storm isn't merely a signal problem. It physically alters the orbital environment, forcing satellites out of their trajectories. Up until now, we've talked about GPS, radio, and satellites, but let's return down to Earth, because one of the greatest risks lies right beneath our feet. A severe geomagnetic storm rapidly shifts Earth's magnetic field, driving geomagnetically induced currents, GICs, through the ground. These unwanted electrical currents flow directly into long conductors, targeting large power transmission grids. According to NOAA, GICs disrupt the operating conditions of high-voltage transformers, overheating core components and triggering widespread grid instability or catastrophic outages under severe conditions. The cascade failure scenario: solar storm hits Earth, leads to magnetic field disturbance, leads to GICs induced in grid, leads to transformer saturation and stress, leads to power grid instability, leads to regional blackouts. However, context is vital here. This does not mean the entire planet plunges into darkness all at once. The true severity of a grid failure depends on several key variables: storm intensity, the raw energy and magnetic orientation of the incoming CME, geographic location. Higher magnetic latitudes near the poles face significantly higher risk. Local geology, ground conductivity alters how GICs flow into local infrastructure. Grid resilience, the specific design, load, and automated protections built into regional power networks.